There is a star 4 light-years away from you right now. Not 4 million, not 4 billion, 4. In cosmic terms, that is nothing. That is the distance between 2 grains of sand sitting on the same table. It is close enough that if the universe were the size of the continental United States, Proxima Centauri would be in the next room. The closest star to our Sun, sitting at a distance so relatively modest that astronomers describe it as our nearest neighbour, the way you might describe the house next door. And orbiting that star, confirmed, measured, real, is a planet. A rocky planet. Roughly Earth-sized. Sitting inside the zone where liquid water could exist on its surface. A world that, by the rough criteria astronomers use to define habitability, qualifies as a candidate, not proven habitable, not confirmed as alive, but a candidate, and the closest candidate to Earth that exists in the observable universe. The planet is called Proxima b, and it has been orbiting its star quietly for billions of years, long before our Sun ignited, long before Earth formed, long before anything on this planet learned to look up and wonder whether anything was out there. And here is the question that changes everything about how you think about space travel, about human ambition, about what it means to be a species standing at the edge of its own cosmic neighbourhood. Can we go there? Not eventually. Not in 1,000 years with technology we cannot yet imagine, funded by a civilization we cannot yet picture. Now, with the physics we understand, with the engineering we can actually contemplate, with human bodies as they actually are, fragile, brilliant, evolved for a single planet, carried in ships that have never travelled further than the moon and back. Can we survive the journey to Proxima Centauri? Can we survive arrival? Can we survive what that planet, with its dim red star and its tidal lock and its radiation environment, and its utterly alien atmospheric chemistry, would do to the bodies of the first people to stand on another world? The answer, when you follow the physics and the biology and the engineering all the way to the end, when you refuse to stop at the easy obstacles and push through to the hard ones, is not the answer science fiction has been giving you. It is more complicated, more specific, more honest, and in some ways more terrifying, and in others more genuinely hopeful, than anything a screenplay has ever been willing to say. This is that answer. But before we begin, if space fascinates you, a like and subscribe means everything to us. Let's begin. To understand why surviving Proxima is so difficult, you first need to understand what Proxima Centauri actually is, not the romantic version, the physical one. Proxima Centauri is a red dwarf star, spectral class M5.5. It has a mass approximately 1/8 that of our Sun, and a luminosity roughly 0.17% of solar, meaning it emits less than 2/1000ths of the light our Sun produces. If you replaced our Sun with Proxima Centauri and kept Earth at its current distance, our planet would be plunged into a darkness colder than the deepest Antarctic winter and would freeze solid within weeks. The star is so dim that despite being the closest star to Earth, it is invisible to the naked eye. You have never seen Proxima Centauri from Earth's surface without a telescope. It exists in the sky, 4 light-years away, entirely invisible, a red coal in the darkness too faint to register on the biological hardware you use to observe the universe. It is part of the Alpha Centauri system, a triple star system that includes Alpha Centauri A and Alpha Centauri B, 2 stars broadly similar to our Sun that orbit each other, with Proxima orbiting the pair at a distance of roughly 0.2 light-years, so far from its companions that whether it is gravitationally bound to them or merely a coincidental neighbour is still technically a matter of debate. Proxima b, the planet, was confirmed in 2016 using the radial velocity technique. Astronomers detected a tiny periodic wobble in Proxima Centauri's movement caused by the gravitational pull of an orbiting planet. From that wobble, they deduced a world with a minimum mass of approximately 1.17 Earth masses orbiting at a distance of just 0.0485 astronomical units from its star, completing one orbit every 11.2 Earth days. That orbital distance is extraordinarily close, closer to Proxima than Mercury is to our Sun. But because Proxima is so dim, that close orbit places Proxima b precisely within the habitable zone, the range of distances at which temperatures could theoretically allow liquid water on the surface. On paper, Proxima b is the most promising nearby target for a planet that could, under the right circumstances, support life as we know it. In practice, the reality is significantly more complicated, and every complication matters if your goal is not just to find Proxima b, but to send human beings there and have them come back alive. The first complication is time, the second is radiation, the third is gravity, the fourth is the atmosphere, or the potential absence of one. The fifth is what the planet's surface environment would actually be like for a body that evolved under a yellow star on a world with a 24-hour day, a global magnetic field, and an oxygen-nitrogen atmosphere it can breathe without assistance. Each of these complications alone is formidable. Together, they constitute the most comprehensive survival challenge in the history of human exploration. Let us begin with the one that everyone acknowledges but almost no one truly confronts: the distance. 4 light-years. The phrase is so familiar, so repeated in astronomy discussions and science documentaries and popular science writing, that it has acquired a kind of comfortable abstractness. It is a large number said in a small way. It is distance dressed in units that make it sound manageable, like something with a definite size you could eventually reach if you simply had the patience. The reality is that 4 light-years is not manageable. It is not simply far. It is far in a way that places it outside every category of distance human civilization has ever navigated. A light-year is the distance light travels in 1 year at 299,792 kilometers per second. 1 light-year is approximately 9.46 trillion kilometers. 4 light-years is approximately 40 trillion kilometers. Written out in miles, it is 25 trillion, a number with 13 digits that has no intuitive meaning, no anchor in human experience, no comparison to anything a human body has ever covered. To appreciate the genuine scale, consider our fastest spacecraft. Voyager 1, launched in 1977, and now the most distant human-made object in existence, is currently travelling at approximately 17 kilometers per second relative to the Sun. This is the fastest sustained velocity ever achieved by a spacecraft, the product of a gravitational assist trajectory so carefully designed that it has never been replicated. At this velocity, Voyager 1 would require approximately 73,000 years to reach Proxima Centauri. 73,000 years. Agriculture was invented 12,000 years ago. Written language is approximately 5,000 years old. Modern physics is 400 years old. The entire recorded history of human civilization, from the first cuneiform tablets in Mesopotamia to the present day, spans roughly 5,000 years, less than 7% of the time it would take our fastest spacecraft to reach our nearest neighbour at its current velocity. The New Horizons spacecraft, which flew past Pluto in 2015 and is now heading toward interstellar space, travels at approximately 14 kilometers per second. At this speed, reaching Proxima Centauri would take roughly 78,000 years. These numbers are not obstacles awaiting better engineering. They are the consequence of a fundamental mismatch between the energy requirements for interstellar travel and the energy sources currently available to human civilization. Chemical rockets, the technology that has carried every human being and every spacecraft off Earth's surface, achieve their velocities through the combustion of propellant. The energy density of chemical propellants is extraordinary by terrestrial standards and utterly inadequate for interstellar travel by any measure that matters. The fastest trajectory currently achievable using chemical propulsion and gravitational assists is approximately 0.006% of light speed. At this velocity, crossing 4 light-years takes the better part of 100,000 years. The crew that departed would be separated from the crew that arrived by more generations than separate us from the first anatomically modern humans. This is not a funding problem, it is a physics problem. It is the problem at the centre of every serious discussion of interstellar travel, and it has no easy solution, only a hierarchy of increasingly ambitious and increasingly speculative partial solutions, each of which comes with its own catastrophic list of survival challenges. Let us examine the most realistic. There are 4 propulsion concepts that serious physicists and engineers consider genuine candidates for interstellar travel within some conceivable human time frame. Not within our lifetime, not necessarily within the next century, but within a time frame short enough that it is worth asking what would happen to the human beings aboard. The first is nuclear pulse propulsion. Project Orion, studied intensively at General Atomics in the late 1950s and early 1960s, proposed using a series of nuclear explosions detonated behind a spacecraft to generate thrust. Small nuclear devices ejected from the rear of the ship, detonated at a calculated distance, would produce plasma that struck a massive pusher plate at the ship's stern, transmitting momentum forward. Shock absorbers between the pusher plate and the crew compartment would smooth the violent impulses into tolerable acceleration. The concept worked in small-scale tests using conventional explosives. The physics was validated, the engineering was challenging but not impossible. Project Orion was killed not by technical failure, but by the 1963 Partial Test Ban Treaty, which prohibited nuclear detonations in space. A nuclear pulse propulsion vehicle optimized for interstellar travel could theoretically achieve velocities between 3 and 10% of light speed. At 10% of light speed, the journey to Proxima Centauri would take approximately 42 years. A crew departing in their 20s would arrive in their 60s, old but alive, and having spent their adult lives inside a spacecraft sustained by the most energetic propulsion system humanity has ever seriously contemplated building. The survival challenges aboard such a vessel would be severe. The nuclear pulse itself would expose the ship to radiation bursts far exceeding safe human limits, unless the shielding was extraordinary. The radiation environment of interstellar space, which we will examine in detail, would be present for the entire 42-year journey with no planetary magnetosphere for protection. The psychological burden of 4 decades of isolation in a sealed environment would be unlike anything in the history of human psychology. But 42 years is survivable in principle. It is a human lifetime spent in a single ship. It is long but not generational. A crew that left would be the crew that arrived. The second concept is nuclear thermal propulsion. Rather than nuclear explosions, nuclear thermal rockets heat propellant, typically liquid hydrogen, by passing it through a nuclear reactor before expelling it through a nozzle. The nuclear heat source allows exhaust velocities roughly twice those achievable with chemical combustion, significantly improving the rocket equation. NASA tested nuclear thermal rockets extensively through the NERVA program in the 1960s and early 1970s, demonstrating that the technology works reliably. Nuclear thermal propulsion could achieve velocities of approximately 0.1% of light speed with reasonable fuel ratios, not enough for a human lifetime crossing to Proxima, but a significant improvement over chemical propulsion and a realistic near-term stepping stone. The third concept is fusion propulsion. Project Daedalus, studied by the British Interplanetary Society from 1973 to 1978, proposed a 2-stage spacecraft burning pellets of deuterium and helium, 3 through inertial confinement fusion. The design targeted Barnard's star at roughly 6 light-years distant, with a cruise velocity of 12% of light speed, achievable in approximately 50 years. Fusion propulsion requires a working fusion reactor, which humanity has been pursuing for decades, and which remains technically challenging but not physically prohibited. Once fusion is mastered, the energy density available for propulsion increases by orders of magnitude over chemical systems. 12% of light speed becomes achievable with fuel ratios that do not require a spacecraft the mass of a small moon. At 12% of light speed, Proxima Centauri is approximately 35 years away. An aggressive fusion architecture, one optimized for maximum velocity at the cost of fuel efficiency, might push that to 25 to 30 years. Still a lifetime's journey, still a commitment that begins and ends with the same crew, but physically survivable in principle if, and this is the word that opens an abyss, if the crew can survive what the universe does to human bodies for 3 decades in deep space. The fourth concept is the most speculative but the most discussed in recent years: laser sail propulsion, the concept at the heart of the Breakthrough Starshot initiative, announced in 2016 with initial funding from Yuri Milner. A ground-based laser array of extraordinary power would focus on a lightweight reflective sail attached to a tiny spacecraft, accelerating it to 20% of light speed in approximately 10 minutes. At 20% of light speed, the journey to Proxima Centauri takes roughly 20 years. But the Breakthrough Starshot concept as currently envisioned is not for a crewed mission. The spacecraft would mass only a few grams, a chip-sized package of sensors, cameras and communication equipment attached to a gossamer sail. It would have no deceleration capability. It would flash through the Proxima system at 20% of light speed, spending perhaps a few hours in the vicinity of the planet before vanishing forever into deep space. Scaling laser sail propulsion to carry human beings introduces challenges that are not yet solved, chiefly deceleration, which a laser-boosted vessel has no mechanism to perform without a second laser array at the destination. But the concept establishes the direction. Beamed energy propulsion is the most plausible near-term path to the velocities at which a crude interstellar mission becomes a human lifetime proposition rather than a generational one. Each of these propulsion systems is real physics. Each has been studied seriously by serious scientists, and each, if implemented, would place human beings in an environment that would begin attempting to kill them the moment they cleared Earth's magnetic field. The journey to Proxima Centauri is the easy part. Surviving the journey is the problem. The most lethal feature of deep space is invisible. You cannot feel it. You cannot taste it or smell it or detect it with any biological sense your body possesses. It does not announce itself with heat or pressure, or the warning signals that biological systems evolved to detect and respond to over billions of years of evolution. It simply arrives, particles moving at significant fractions of light speed, carrying energies millions of times greater than the photons of visible light, and passes through everything in its path, including you. Cosmic radiation is the dominant existential threat to human survival in deep space, and it comes in two distinct forms, each dangerous in different ways and on different timescales. The first is galactic cosmic rays. These are charged particles, primarily protons and heavier atomic nuclei, accelerated to near-light velocities by supernova shock waves, magnetar flares, and other violent astrophysical events scattered throughout the galaxy. They arrive from all directions continuously, streaming through interstellar space with an isotropy, an equal distribution in every direction quality, that means there is no shielding direction. No matter which way you point your spacecraft, galactic cosmic rays are arriving from that direction too. Their energies are extraordinary. The most energetic galactic cosmic rays carry energies exceeding 10 to the 20th electron volts, energies so extreme that individual particles carry the kinetic energy of a baseball thrown at 100 kilometers per hour. A single high-energy cosmic ray passing through a cell can shatter DNA strands, disrupt chromosomes, trigger the cascade of genetic damage that initiates cancer, or kill the cell outright. Most individual impacts are repaired by cellular repair mechanisms, but those repair mechanisms have a finite capacity. Above a certain cumulative dose, they are overwhelmed. Damage accumulates faster than it is repaired. The cellular machinery begins to fail. Inside Earth's magnetic field, galactic cosmic rays are significantly attenuated. The magnetic field deflects charged particles, particularly lower energy ones, into polar regions where they spiral down into the upper atmosphere and are absorbed. The atmosphere itself provides additional shielding, equivalent to approximately 10 meters of water in radiation protection terms. A human being standing on Earth's surface receives a background galactic cosmic ray dose of approximately 3 millisieverts per year, low enough that the body's repair mechanisms handle it without difficulty throughout a normal lifetime. In deep interstellar space, outside the heliosphere, beyond the magnetic protection of both Earth and Sun, the galactic cosmic ray flux increases substantially. Current estimates based on measurements from Voyager 1 and 2, which have crossed the heliopause and entered interstellar space, place the interstellar cosmic ray flux at roughly 30% higher than the flux within the heliosphere. Astronauts on a deep space mission would receive annual radiation doses of approximately 600 to 900 millisieverts from galactic cosmic rays alone. Doses that, sustained over decades, would dramatically increase cancer risk and could cause radiation-induced cataracts, cardiovascular damage, and neurological deterioration. The second form of cosmic radiation is solar energetic particle events, massive eruptions of charged particles from the Sun's corona during solar flares and coronal mass ejections. These events are unpredictable and can deliver acute radiation doses in hours or days that exceed the levels associated with radiation sickness. On Earth, and even within the near-Earth radiation environment experienced by astronauts on the International Space Station, solar energetic particle events are dangerous but manageable. The International Space Station has a dedicated shelter, a small, heavily shielded module where crew can take refuge during major solar events. The shelter provides enough protection for the duration of most events. casualties aboard the ISS from radiation have been zero. In deep space, a major solar energetic particle event without adequate shielding would be a survival emergency of the highest order. Doses of several sieverts delivered over hours cause acute radiation syndrome, nausea, vomiting, immunosuppression, and at sufficiently high doses, death within days to weeks. The treatment for acute radiation syndrome requires bone marrow transfusions, aggressive antibiotic therapy, and intensive medical care, none of which is available in a spacecraft 40 trillion kilometers from the nearest hospital. Shielding against cosmic radiation is the central engineering challenge of crewed interstellar missions, and it has no fully satisfying solution. The physics of radiation shielding is well understood. Dense materials, water, polyethylene, lead, absorb and scatter charged particles, attenuating the radiation reaching the shielded volume. Water is particularly effective because its hydrogen content makes it an excellent absorber of proton radiation, and it serves the dual purpose of life support supply. A water shield 2 meters thick surrounding the crew habitat would provide substantial protection against solar energetic particles and lower energy galactic cosmic rays, but high energy galactic cosmic rays are extraordinarily penetrating. Above a certain energy threshold, adding more shielding material actually increases the radiation dose on the other side, because the primary cosmic ray, striking the shielding material, produces a shower of secondary particles that collectively deliver more dose than the original primary would have. This phenomenon, called nuclear spallation, means that passive shielding has an optimal thickness above which it becomes counterproductive. Active magnetic shielding, generating an artificial magnetic field around the spacecraft analogous to Earth's magnetosphere, could deflect charged particles before they reach the hull. The technology required is theoretically sound. Superconducting coils generating a field of several Tesla, maintained at cryogenic temperatures around the crew module, could reduce the cosmic ray dose substantially. The engineering challenge is maintaining superconductivity over decades in an environment with temperature fluctuations and micrometeorite strikes, generating the power required to sustain the field, dealing with the structural loads imposed by the magnetic forces, are formidable but not physically prohibited. Even with optimal passive shielding combined with active magnetic shielding, a crew on a 30-year journey to Proxima Centauri would accumulate radiation doses that current regulatory limits for astronaut lifetime radiation exposure would classify as unacceptably high. NASA's current career radiation limit for astronauts is 600 millisieverts, a limit derived from acceptable excess cancer risk thresholds and designed for careers of a few years in low Earth orbit. A 30-year interstellar transit at estimated deep space flux rates, even with aggressive shielding, would deliver doses several times that limit. The crew would not die of radiation on the journey. The doses, while high, are not immediately lethal. They are chronically damaging. They shorten life expectancy, elevate cancer risk, accelerate cardiovascular disease, and cause neurological deterioration that compounds with other deep space health effects. They make a difficult journey significantly more dangerous for the travelers who complete it, and radiation is only the first problem. The second assault on the human body in deep space is gravity, specifically its absence, or rather, the absence of the gravitational acceleration that every system in your body was calibrated for before your first breath. Microgravity, the near weightlessness experienced in free-falling orbital environments, does things to human physiology that are still being fully catalogued after 60 years of spaceflight experience. The International Space Station has been continuously inhabited since November 2000. The cumulative medical data from ISS crews is the most comprehensive picture available of what long-duration microgravity does to the human body, and what it shows is a systematic, progressive deterioration of essentially every physiological system that your body maintains using gravity as a signal. Begin with the bones. Bone tissue is not static. It is constantly being rebuilt by cells called osteoblasts, which lay down new bone matrix, and broken down by cells called osteoclasts, which resorb old or damaged bone. In a healthy adult under gravity, these two processes are in approximate balance. Bone density is maintained at levels adequate for the structural demands of life on Earth's surface. The signal that tells osteoblasts to keep building bone is mechanical loading. The stress transmitted through bone tissue by the weight of the body and the forces of muscle contraction against gravity. Remove gravity and that mechanical loading disappears. The osteoblast signal weakens, the osteoclasts continue their resorption. The balance tips. Bone mineral density begins to decline at approximately 1 to 2% per month in the weight-bearing bones of the lower spine, hips and legs, the bones that, on Earth, are most continuously loaded. After 6 months aboard the International Space Station, astronauts have lost an average of 10 to 15% of bone mineral density in the lower spine and hip, losses equivalent to decades of osteoporotic deterioration compressed into months. Most of this loss is recoverable with aggressive rehabilitation after return to Earth, but recovery is slow and incomplete for the most affected individuals. Over a 30-year interstellar transit in microgravity, the skeletal deterioration would be catastrophic and irreversible. Without continuous mechanical loading, bones do not merely weaken, they remodel, changing their architecture in response to the actual mechanical demands they experience, becoming structures optimized for a zero-gravity environment that bear little resemblance to the bones required for life on a planet's surface. By the time a crew arrived at Proxima b, their skeletal systems would be so thoroughly adapted to weightlessness that standing upright in any meaningful gravitational field might be structurally impossible. The solution is artificial gravity, rotating the spacecraft or sections of it to generate centripetal acceleration that mimics gravitational loading. This is not exotic technology. It is straightforward mechanical engineering. A rotating habitat of adequate radius, spinning at an appropriate rate, can generate one Earth gravity of centripetal acceleration with modest engineering complexity. The catch is the radius and rotation rate. At short radii, 10 to 20 meters, the rotation rate required to generate one gravity is high enough to cause motion sickness and disorientation in most people, because the Coriolis effects experienced moving through the rotating reference frame are strong enough to conflict with the vestibular system's sense of orientation. At longer radii, several hundred meters, the required rotation rate is low enough to be physiologically tolerable, but the structural requirements for a spacecraft of that scale are engineering challenges of their own. The consensus among space medicine researchers is that an artificial gravity habitat with a radius of at least 225 meters, rotating at approximately 2 rotations per minute, would produce a gravitational environment that most humans can adapt to without significant Coriolis-induced disorientation. This is achievable. It requires a significantly larger spacecraft than any currently proposed, but it does not require new physics. Without artificial gravity, a crew could supplement partial gravitational loading through rigorous exercise, resistance training and aerobic exercise programs that apply mechanical loads to the skeleton and cardiovascular system. Current ISS protocols require 2 hours of structured exercise per day to partially offset the skeletal and cardiovascular effects of microgravity. Even with this aggressive regimen, bone and muscle losses accumulate over long missions. Over 30 years, no exercise protocol would be sufficient. Artificial gravity is not optional for a crewed interstellar mission, it is a survival requirement. The third assault on the human body in deep space is the one that is hardest to engineer around, hardest to treat, and hardest to predict in advance for any given individual. It is psychological, and it is profound. Human beings evolved as social animals in small groups, embedded in environments rich with sensory information, light and sound and smell and temperature variation, and the sight of the horizon, and the feel of wind and the biological rhythms of day and night and season and year. Human psychology is calibrated for these conditions with the same precision that human physiology is calibrated for gravity. Remove them, and the mind, like the skeleton, begins to deteriorate in specific, measurable, predictable ways. The psychological research on long-duration isolation is extensive. Antarctic overwintering stations, facilities where small crews spend months in near-total isolation during polar winter, provide the closest terrestrial analogue to crewed interstellar missions. The psychological effects documented in Antarctic winter over crews include a specific syndrome sometimes called the winter over effect or the third quarter phenomenon, a period of reduced motivation, impaired cognitive performance, interpersonal conflict and emotional dysregulation that consistently appears roughly 2/3 of the way through the isolation period, then gradually resolves as the end of the mission approaches. In an Antarctic station, the end is always known. The supply flights will arrive, the winter will end, the isolation is finite. crew members can sustain motivation by counting down to a definite conclusion. On a 30-year journey to Proxima Centauri, the structure of that psychological support is entirely different. The crew departed, knowing that the mission will occupy most or all of their remaining active lives. The midpoint of the journey 15 years in is not a relief, but a psychological landmark that marks the irrevocability of the commitment. The only conclusion is arrival, and arrival means beginning the equally demanding work of survival on an alien planet. Research from simulated isolation studies, including the Mars 500 experiment conducted at the Institute for Biomedical Problems in Moscow, which locked 6 crew members in a simulated Mars spacecraft for 520 days, documents specific cognitive impairments associated with long-duration confinement. Sleep disruption increases. Reaction time slows. Attention and working memory degrade. Conflict between crew members escalates. Depression prevalence rises. At the extreme end, durations and conditions more severe than any study has yet ethically imposed on human subjects. The projection is that long-term psychological function deteriorates to a degree that compromises the crew's ability to operate and maintain the ship. The crew selection challenge for an interstellar mission is unlike anything in the history of human psychology. Not selecting for courage or technical skill or physical fitness, though all of those matter, but selecting for psychological resilience across a timescale of decades under conditions of irreversible commitment. In a group so small that every interpersonal dynamic plays out with no possibility of escape or relief. Research on optimal crew size for long-duration isolated missions consistently suggests that groups of 4 to 6 people provide the best balance between maintaining social complexity sufficient to prevent depression and isolation, and keeping populations small enough to avoid factional conflict and resource strain. 6 people is small enough that every interpersonal relationship is constantly salient for 30 years. The neurological dimension of deep space psychology is made worse by the radiation environment. Galactic cosmic rays do not just damage DNA, they damage neurons. Studies in mice exposed to simulated galactic cosmic ray radiation show measurable cognitive impairment, reduced performance on spatial learning tasks, increased anxiety behaviors, disrupted neurogenesis in the hippocampus at doses comparable to what a crew would receive during an interstellar transit. The neurological damage from chronic radiation exposure may amplify and accelerate the psychological deterioration from isolation, creating a compound threat to cognitive function that is more severe than either factor alone would produce. The crew arriving at Proxima b after 30 years of radiation exposure, isolation, and the relentless physiological stress of deep space would not be the crew that departed. They would be older, physiologically compromised by the accumulated effects of the journey, and neurologically altered by cosmic ray exposure in ways that are not yet fully characterized. Whether they would still be cognitively capable of the complex, high-stakes work of exploring and surviving on an alien planet is a question that current research cannot answer with confidence. Assume the crew survives the journey. Assume the radiation shielding is adequate. Assume artificial gravity maintains skeletal and cardiovascular health. Assume careful crew selection, psychological support protocols, and perhaps pharmaceutical interventions preserved cognitive function through 3 decades of isolation. Assume the ship's systems held together across 40 trillion kilometers of deep space without a catastrophic failure. They arrive at Proxima b, and they discover that the journey was the easy part, because Proxima b sits inside the habitable zone of a star that is actively trying to sterilize it. Proxima Centauri is not a calm, stable, middle-aged star like our Sun. It is a flare star, one of the most active subclasses of red dwarf, characterized by frequent, violent, unpredictable eruptions from its surface that release bursts of X-ray and ultraviolet radiation powerful enough to overwhelm the protection of any plausible planetary atmosphere. In May 2019, astronomers monitoring Proxima Centauri with a network of telescopes observed a flare event so powerful it briefly increased the star's brightness by a factor of 14,000 in ultraviolet wavelengths. In a period of approximately 7 seconds, Proxima Centauri released an amount of UV radiation equivalent to what our Sun releases in a comparable UV outburst, but at a planet orbiting much closer, receiving a proportionally far more intense dose. If Proxima b has an atmosphere, it is under constant assault from these flare events. Extreme UV and X-ray radiation from flares drives atmospheric escape, stripping gas molecules from the upper atmosphere and ejecting them into space through a process called photoionization, followed by ion pickup by the stellar wind. Mars lost most of its atmosphere through a similar process when its magnetic field collapsed and the solar wind began eroding it directly. Whether Proxima b retains an atmosphere at all is genuinely unknown. The planet was detected through radial velocity measuring the star's wobble. No direct observation of the planet's atmosphere has been made. Models offer a wide range of possibilities. If the planet formed with a substantial water and volatile inventory, if it migrated to its current position after the star's most active young phase had ended, if it has a strong enough internal magnetic field to partially shield its atmosphere, it might retain enough of an atmosphere to be relevant for human survival considerations. If it does not have a meaningful atmosphere, the surface of Proxima b is essentially unshieldable by any plausible human technology. The radiation environment on an airless planet at Proxima b's orbital distance would be lethal on timescales of minutes during flare events and chronically damaging between them. No surface habitat could protect occupants from the cosmic radiation environment without effectively being an underground bunker and building underground habitats on another planet with the resources available on an early interstellar mission is not a realistic near-term possibility. If Proxima b does retain an atmosphere, the composition matters enormously for human survival. An oxygen-nitrogen atmosphere similar to Earth's would be a near-miraculous stroke of luck, one that astrobiologists consider vanishingly unlikely, given the differences in stellar type and the planetary formation. Environment. More plausible atmospheric compositions for a Proxima b with a surviving atmosphere include water vapor and carbon dioxide, nitrogen and trace gases, or exotic chemistries dependent on the outgassing history of the planet's crust, and the photochemistry driven by Proxima's specific radiation spectrum. None of these alternatives is breathable by unaugmented humans. Any crew on the surface of Proxima b would require a sealed pressure suit at all times outside a habitat, a severe operational constraint for any exploration or survival activity, and a catastrophic single-point failure mode if the suit is breached or the habitat loses integrity. There is an additional feature of Proxima b's environment that makes its surface unlike any environment humans have experienced preparing for. Proxima b is almost certainly tidally locked to its star. Tidal locking is what happens when one body orbits another closely enough that the gravitational tidal forces slow the orbiting body's rotation until its rotational period matches its orbital period. The same face always, pointing toward the central body. The Moon is tidally locked to Earth, the reason we always see the same side of the Moon. Proxima b, orbiting its star at a distance of only 0.0485 astronomical units with an orbital period of 11.2 days, would have been tidally locked within a geologically short period after formation. A tidally locked planet is a world of radical environmental extremes. One hemisphere faces the star permanently the day side. It receives continuous stellar radiation, never experiencing night. Temperatures on the day side depend on the atmosphere, but on a world with a significant atmosphere, the constant stellar input would produce a persistent hot zone centered on the substellar point, the location directly beneath the star, where temperatures could be substantially higher than the planet's average. The opposite hemisphere faces permanently away from the star, the night side. It receives no stellar radiation. On an airless world, the night side would cool to temperatures approaching the cosmic background minus 270 degrees Celsius. On a world with a substantial atmosphere, atmospheric circulation would transport some heat from the day side, moderating the night side temperature significantly, but the night side would still be dramatically colder than the day side. Between these two extremes lies the terminator, the ring-shaped boundary between the permanent day and permanent night hemispheres. On a world with an atmosphere, atmospheric models suggest the terminator region might be the most potentially habitable location, receiving scattered and refracted stellar light, rather than direct radiation, experiencing temperatures moderated by the circulation of both dayside heat and nightside cold, and potentially sheltering liquid water in the narrow band where conditions are neither scorched nor frozen. The terminator of Proxima b, if the planet has an atmosphere and liquid water, is where any surface habitat would need to be located. A strip of world perhaps a few hundred kilometers wide, circling the entire planet, where the alien sun hangs perpetually on the horizon, never rising fully overhead, never setting, casting a permanent twilight across a landscape that has no day or night as humans have ever experienced. The psychological implications of this environment deserve serious attention. Human circadian biology is calibrated for a 24-hour light-dark cycle. Disrupting that cycle as Antarctic winter over crews experience during polar night and polar day produces measurable hormonal disruptions, sleep disorders, mood dysregulation, and cognitive impairment. Life in a permanent twilight environment with no day-night cycle at all would impose a continuous circadian disruption that no human population has ever adapted to. Artificial lighting systems inside habitats could simulate light-dark cycles, but the moment any crew member stepped outside the habitat, the light environment would be the alien Terminator twilight, a perpetual dim glow from a star forever perched on the horizon. The gravity of Proxima b is also uncertain. The radial velocity technique measures minimum mass. The mass, assuming the planet's orbital plane, is edge-on to our line of sight. If the orbital plane is inclined, the true mass could be higher. Models suggest Proxima b's surface gravity is probably somewhere between 0.8 and 1.3 Earth gravities, depending on the planet's bulk composition and true mass. A surface gravity of 1.3 Earth gravities, a possible upper bound, would impose a continuous physiological stress on a crew whose bodies spent 30 years adapted to 1 Earth gravity of artificial gravity. 13% additional weight sounds modest. Sustained over years, it is the equivalent of carrying a backpack weighing 13% of your body mass every moment of every day. It causes fatigue, joint stress, and cardiovascular strain. In isolation, it is manageable. Combined with the radiation exposure, the psychological stress, and the alien atmospheric environment, it is one more compound in a cocktail of physiological challenges that accumulates toward a threshold. There is a dimension of survival at Proxima b that is not physical or physiological, it is informational. And its implications are so far-reaching that they constitute their own category of existential challenge. Communication with Earth from Proxima Centauri is limited by the speed of light. Radio signals travel at light speed. The distance from Proxima Centauri to Earth is 4.25 light-years. A message sent from Proxima b takes 4.25 years to arrive at Earth. Earth's reply takes another 4.25 years to arrive at Proxima. A complete round-trip communication question and answer takes 8.5 years. This is not a technology problem awaiting a faster solution. No known physics permits faster than light communication. The 8.5-year round trip is a fundamental physical constraint, not a bandwidth limitation. For a crew on Proxima b, the practical consequences of this constraint are radical. Any medical emergency requiring consultation with Earth-based expertise faces an 8.5-year round-trip delay for the advice to arrive. Any technical malfunction requiring engineering guidance from Earth-based specialists faces the same delay. Any political or ethical decision requiring input from the civilization that funded and launched the mission faces an 8.5-year turnaround. The crew at Proxima b would be, in every practical sense, entirely autonomous. Every decision, medical, technical, ethical, political, would need to be made by the crew themselves, with whatever knowledge and expertise they carried from Earth, augmented by whatever information they could extract from a data archive of books, manuals, medical databases, and scientific literature uploaded before departure. The crew would need to contain, among its members, comprehensive expertise in medicine, surgery, engineering, geology, biology, chemistry, physics, agriculture, and psychology, because any gap in that expertise is a gap in their survival capability, and there is no calling for help. They would also need to be entirely self-sufficient in material terms. Every component that breaks must be repaired with what is available on the ship, or produced locally on Proxima b. Every medical crisis must be treated with what is aboard. The luxury of a supply chain, the invisible infrastructure of replacement parts and pharmaceuticals and fresh food, that sustains every human settlement on Earth does not exist across 4.25 light-years, the psychological weight of this absolute self-sufficiency would be profound. Humans are extraordinarily poor at assessing their own limitations under stress. The crew members who maintain the most critical survival systems, the ship's reactor, the habitat pressurization, the medical suite would carry a burden of personal responsibility that no human institution has yet developed reliable methods for sustaining over decades. And Earth would be watching. The signals from Proxima b status updates, scientific data, crew messages would arrive at Earth 4.25 years after transmission. The civilization following the mission from Earth would be watching a movie of the mission 4.25 years behind real time, unable to intervene, unable to help, able only to observe and transmit advice that will not arrive for years. The crew at Proxima b would know this. They would know that the voices they receive from Earth are voices of people who are 4.25 years older than the words they hear. That the people who launch them are aging, some dying, civilization changing, while the crew lives in a present that Earth will not learn about for years. The isolation is not just physical, it is temporal. The crew at Proxima b are living in a present that Earth cannot access in real time and never will separate it from their origin, not just by distance, but by the irreducible delay of light speed across 4 light-years of empty space. Assume the crew survives the journey, the radiation, the psychological deterioration, and the communication silence. Assume they land on Proxima b and establish a habitat on the Terminator. Assume the planet has an atmosphere not breathable, but present and dense enough to provide some shielding from stellar radiation. Assume the surface gravity is manageable. The next survival challenge is one that no human has ever faced, and that no amount of Earth-based preparation can fully anticipate. Contact with an alien biological environment. Proxima b, if it has liquid water and an atmosphere and conditions in some range of habitability, may have life, not intelligent life, not even necessarily complex multicellular life, but microbial life, the baseline biological output of planets where the chemistry and energy sources are adequate, is a genuine possibility. And microbial life on Proxima b, if it exists, would have spent billions of years evolving in a chemistry under a radiation spectrum at temperatures and pressures shaped by a planetary history entirely unlike anything on Earth. Proxima b's biology, if it has any, would be alien in a precise technical sense, not alien meaning strange or unfamiliar. Alien meaning built from a potentially different molecular alphabet, using different metabolic pathways, operating under different chemical constraints, and capable of interactions with human biology that are entirely uncharacterized and entirely unpredictable. The greatest biological threat might not be pathogens in the conventional sense, organisms that evolve to infect a host, develop mechanisms for evading immune defenses, and cause disease through specific pathological mechanisms. That kind of biological threat requires a shared evolutionary history. A terrestrial pathogen is dangerous to humans because it evolved in an environment containing human biology and developed strategies optimized for exploiting human biochemistry. An alien microbe from Proxima b evolved with no knowledge of human biology. It has no mechanisms optimized for infecting human cells because it has never encountered human cells. In this sense, the risk from alien pathogens might be lower than from familiar terrestrial ones. But the risk from alien biochemistry is different and potentially more serious. Alien metabolic byproducts, chemicals produced by alien microbes as part of their normal biochemistry, might be profoundly toxic to human biology without anyone having evolved any particular intention of harm. A microbe that exhales a compound that is entirely benign in its native chemistry could exhale that compound into a habitat where it reacts with human enzyme systems in ways that are lethal, not through infection, through straightforward chemical toxicity. The sealing protocols for early Proxima b exploration would need to be absolute. Full pressure suits at all times outside sealed habitats, airlock decontamination procedures between every excursion, biological monitoring for any crew member showing signs of chemical exposure, air filtration systems capable of removing any particulate biological material from habitat air before it is recycled to the crew. And despite all of this, Some contact is probably inevitable over years of surface operations. The crew would be living in a biological environment, breathing recycled air that passed through filtration systems, eating food grown in sealed hydroponics, drinking water processed through purification systems that remove biological material. The filtration systems are very good. They are not perfect. Over years, some exposure will occur. The immune systems of the crew, already compromised by years of radiation exposure, sleep disruption, and the chronic physiological stress of deep space, would face this exposure without any evolutionary preparation whatsoever. No immune response that evolved on Earth was shaped by selective pressure from Proxima b biology. There are no antibodies, no innate immune recognition patterns, no adaptive immunity pathway that can be called on. The crew's biological encounter with Proxima b's environment would be the first such encounter in the history of life on Earth, and it would be happening in real time on a planet 4.25 light-years from any hospital, with no possibility of calling for help. We have now walked through every major survival challenge of a crewed mission to Proxima Centauri. Let us stop and look at the list. Radiation across 30 years of interstellar transit requiring active magnetic shielding and passive water shielding of significant mass and engineering complexity, reducing but not eliminating cumulative dose to levels that meaningfully elevate cancer risk and neurological damage. Microgravity over 30 years requiring a rotating habitat of adequate radius to generate artificial gravity sufficient to prevent skeletal and cardiovascular deterioration, a structural engineering challenge of the first order. Psychological deterioration across decades of isolation requiring crew selection processes and psychological support protocols of unprecedented rigor, pharmaceutical interventions to maintain circadian rhythm and mood regulation, and a crew composition carefully optimized to sustain interpersonal function over timescales that dwarf any previous isolated mission. Tidal locking and extreme surface environment, requiring a landing site in the narrow terminator zone, sealed habitats capable of maintaining Earth-standard pressure and atmosphere indefinitely, full pressure suits for all surface operations, and surface power systems capable of sustained operation without a day-night solar cycle. Flare radiation at the planetary surface requiring radiation shelter capabilities within the habitat, real-time monitoring of stellar activity, and operational protocols that move crew to shielded areas during major flare events with sufficient warning time. Communication isolation requiring total crew self-sufficiency across every discipline required for survival, comprehensive medical and technical expertise within the crew, and the psychological resilience to operate without external guidance or support for the entire duration of the mission. Alien biological environment requiring absolute sealing protocols, advanced filtration and decontamination systems, biological monitoring, and the management of immune responses to an environment for which human biology has no evolutionary preparation. This list is not the list of problems that prevent a mission to Proxima Centauri. It is the list of problems that must be solved to make such a mission survivable. Every item on it has a physical solution, not a convenient solution, not an inexpensive solution, not a solution that can be implemented with near-term technology, but a solution that does not require new physics, only new engineering, new materials science, new medicine, and the sustained commitment of a civilization willing to spend what the mission actually costs. What it costs is not primarily money. Money is the abstract representation of resources and human effort. What it costs is time, decades of sustained research and development in propulsion, radiation medicine, closed-loop life support, human psychology, planetary science, and a dozen other fields that must advance in concert before a crewed mission to Proxima is survivable rather than suicidal. It costs the willingness to treat interstellar travel not as a distant dream, but as an engineering project with requirements, milestones, budgets, and the same kind of systematic development that took humanity from the Wright Flyer to the Apollo program in 66 years. It costs, above all, the honest acknowledgement of how hard this actually is. The replacement of the science fiction vision of interstellar travel, romantic, swift, populated by heroes who survive because the plot requires it, with the scientific vision. The one where the physics is precise and the biology is unforgiving, and the survival is not guaranteed but is worth attempting. And yet the question at the center of this entire journey, can we survive? Proxima has an answer that the survival challenges alone do not determine. Because survival is not the only variable. Survival is the threshold condition, the minimum requirement below which the mission is pointless. But above that threshold, the question is not whether we can survive, but whether we will go. And that question is not answered by physics or biology or engineering. It is answered by something older than any of those disciplines, something built into the structure of whatever it is that makes us the species that looks up. Human beings have never, in the entire recorded history of our existence, encountered a frontier and stopped at it permanently because the crossing was difficult. The history of human exploration is the history of crossing frontiers that the available technology was inadequate for, and building the technology to make the crossing anyway, because the alternative, the staying, was considered worse than the risk of going. The crossing of the Bering Land Bridge, the settlement of the Pacific by Polynesian navigators in open canoes, using star navigation and wave patterns, and the flight paths of birds to cross an ocean with no map. The first voyage around the Cape of Good Hope, the overland crossing of the American continent, the first flight, the first orbit, the first steps on another world. Every one of these crossings was attempted before the technology was fully adequate. Every one resulted in casualties. Every one was made by human beings who knew the risk was real and went anyway, not because they were reckless, but because they understood, with a clarity that precedes rational argument, that the going was more important than the safety of staying. Proxima B is the next frontier in that sequence, the same species, the same drive. The survival challenges are real, the radiation is real, the distance is real, the tidal locking and the alien biology and the communication silence are all real. We have spent this entire journey mapping them honestly, without romanticizing them and without pretending they are smaller than they are. But here is what is also real. Proxima B has been there, orbiting its dim red star, for billions of years. For billions of years it has existed without anyone, as far as we know, ever arriving to find out what it is. It has a surface, it may have an atmosphere, it may have water, it may have life. It contains answers to questions that we cannot answer from here. Questions about the distribution of life in the universe, and the range of environments that biology can inhabit, and the nature of planetary development around red dwarf stars. And it is 4 light years away. 4 light years, in cosmic terms, an arm's reach. In engineering terms, a challenge of the first order that will require a century of technological development, and the commitment of a civilization willing to invest across generations. In human terms, in the terms of what it means to be a species that looks up and asks whether it can go there, it is the next step. The survival challenges will be solved, not because they are easy, because they are in front of us, and we are the species that solves what is in front of us when the reason to solve it is compelling enough. And the reason to solve this one is compelling enough. Imagine the moment. 30 years out from Earth, the ship decelerating fusion engines firing in reverse, burning fuel accumulated at the journey's midpoint, trading velocity for approach trajectory. Through the observation port, a dim red star growing imperceptibly brighter as the distance closes, and beside it, barely visible, a planet. Not Earth. Not anything like Earth. A world tidally locked to its star, one hemisphere in perpetual day, one in perpetual night. The Terminator line between them, a permanent twilight that circles the planet like a ring. A surface that has never been touched by a human footstep, an atmosphere whose composition is still, even now, being refined by the ship's spectrometers as they read the starlight filtering through it on approach. The crew is old. They were young when they left. They are not young now. Their bodies carry 30 years of deep space, the radiation, the artificial gravity, the accumulated stress of 3 decades inside a sealed hull, moving through the dark between stars. Their bones are somewhat thinner than they were. Their eyes carry the slight cataracts of chronic radiation exposure. Their minds are shaped by 30 years in a community of 6, by the long middle passage through the dark, by the weight of knowing they left and did not come back. But they arrived. The first humans to cross the gap between stars. The first humans to look at a world not illuminated by the sun. The first humans to see, with their own eyes, a planet lit by a different star, orbiting in a different system, belonging to a different part of the galaxy. The first humans to be, in any physical sense, somewhere else. The planet below them may be dead. It may be barren. It may be so hostile that they will spend only weeks before the evidence forces them to concede that human survival there, at this technological stage, is not sustainable. Or it may have something, some trace, some signature, some indication of complexity in its chemistry that justifies another generation of missions, another generation of engineering development, another century of trying. They do not know yet. They are still approaching, but they are there, 4 light-years from Earth, in the glow of a red star, looking down at a world that humanity has wondered about since the night it first learned to count the stars. The answer to the question, can we survive Proxima, was never simply yes or no. It was, we go, we find out, we survive what we can, we learn what we came to learn, and we carry it back to the civilization that sent us. That is what exploration means. That is what it has always meant. And Proxima has been waiting long enough.